We're now going to take a look at a different type of fluid. We just talked about Newtonian fluids. We're now going to look at non-Newtonian fluids. So when we're dealing with non-Newtonian fluids, tau is not a linear relationship with the shear rate. And so if you recall for Newtonian, we had the constant of proportionality being viscosity, and we had this. That is for Newtonian. And so you can imagine if you were to plot tau versus du by dy, you would have a linear relationship. Well, for non-Newtonian fluids, you don't have a linear relationship. And so there are different types of fluids that exist with different characteristics. The study of this is called rheology, looking at the shear rate and shear stress relationships. But we'll take a look at non-Newtonian fluids in this segment. And what we'll do is we'll begin with a plot of shear stress versus shear rate. And so we'll put tau, or shear stress, on the vertical. And we will put shear rate, or du by dy, on the horizontal. And we talked about Newtonian, so that would be here. Now we can have other types of fluid behaviors. One type is referred to as being a pseudoplastic fluid, and with that one, the higher the shear rate, the shear stress starts to be reduced. And it would have a characteristic that would look kind of like that. And that is what we call a pseudoplastic. And a common example of a pseudoplastic that is often referenced is common latex paint. If you think about when you're painting, when the paint is just sitting on the brush, it doesn't really drip very quickly. However, when you start to apply it to the wall, you apply a lot of stress, and then the shear stress in the fluid is actually reduced, and so it becomes easier to apply the paint. And so sometimes that's with complex molecular structures, you'll find that you get that characteristic. But paint, latex paint, is a pseudoplastic. Another type of fluid where the more shear you apply, the higher the shear stress. That is what we would call a shear thickening or a dilettante. And that is shear thickening. And a common fluid that has that attribute would be water and cornstarch. So pseudoplastic down here, that is a shear thinning. The higher the shear rate, the lower the shear stress. And then shear thickening, a water cornstarch mixture. Newtonian we have here. And then a final form that is quite common that exists, and it's one that we all probably use every day, is toothpaste. And with toothpaste, when you think about it, is toothpaste a solid or is it a liquid? Well, we all know that if we squeeze the tube, the toothpaste comes out, so it's obviously flowing. But in the room state, if it's just sitting there, toothpaste doesn't move. And so toothpaste requires a certain amount of shear stress before it begins to flow. And that is what we call a Bingham plastic. So let's draw a Bingham plastic. The attribute of a Bingham plastic is that you need to apply a certain shear stress before it begins to flow. And you would call that the yield stress. And then once you achieve that, then the fluid starts to flow. So that would be a Bingham plastic. And the most common one is toothpaste. And the attribute is that it requires a certain amount of shear, a yield stress, before it starts to flow. So there are a number of different fluids. In this course, we're not going to look at non-Newtonian fluids because it's quite complex. The nonlinear relationship makes the equations that we deal with, which we'll see will be the Navier-Stokes equations, quite complex. So for the most part, what we'll be doing is restricted to Newtonian flows, which are in here, and have a nice linear relationship. Recall it's the tau equals mu du by dy. But it's important that you realize that not all fluids follow that characteristic. There are others, dilettantes, pseudoplastics, Bingham plastics, that have a nonlinear relationship, and we call those fluids non-Newtonian.